Okay, I'm going to get started today. So good morning, everybody. Welcome to a special edition of our usual lecture time due to the fact that my internet went out yesterday for a few hours. So what I'm going to do now is I'm going to finish up the lecture that we started yesterday. So this is going to go basically straight on YouTube. So I'm on Zoom right now, but it looks like no one else is here, but that's okay. So again, I apologize, for this format, and I know this isn't ideal. Ideally, you guys would all be here so you can ask questions kind of in real time as I'm doing the notes. But due to the internet being out yesterday, there was, it didn't come back on until after 8:30 yesterday. So, so again, I apologize, and of course, I'm available anytime for questions, either via email or if you want to talk either in office hours or make a Zoom appointment. I'm always available for that. So, okay. So let's go ahead and get started. So it was actually, really convenient yesterday that we kind of cut off kind of right at the end of the 2D convection with finite volumes, and we're just about to get into higher order schemes. So let's go ahead and do that. Okay. So this is starting a new lecture note. So if you go on Titanium, then you should see lecture notes for higher order convection schemes, and that's basically what we're starting now. Okay. So to kind of prep or to kind of introduce this, I want to kind of remind you guys that out of all the terms that we've had to discretize, or all the terms that we had to deal with in our kind of general equation that we've been working with this semester, convection seems to be the most tricky, which is really I guess not intuitive, because in terms of complexity, the convection derivative is just a first order derivative. But let me just kind of remind you of some of the issues that we've had before. Okay. So the first one is the fact that if you're using some kind of central scheme, whether that's central difference or the or kind of the simple averaging that we did for finite volumes, what you're subject to is that it's possible that your simulation will be unstable. Okay. So we've already looked at different ways that we can fix this. So there's we looked at two different ways. So the first way that we went over was we can check the Peckley number. So if you can refine your mesh enough, or make delta x small enough such that the Peckley number is less than 2, that's one way to make your simulation stable. The other way to make it unconditionally stable is to use an upwinding scheme. So in finite difference, we saw that by using the backward difference scheme for our derivative, and then for finite volumes, we just saw that we can do this by kind of using the upwinding cell instead of the average between the central cell and the neighbor cell. So we already kind of know how to deal with this within reasonable bounds. But the other kind of big problem that that we saw when we covered this in finite differences is that we had this phenomenon known as the artificial diffusion, or crosswind diffusion. Okay, and this only occurred in 2D and 3D. Okay. Okay. And so if you recall, the reason that we had this phenomenon was the fact that in 2D and 3D, we can have this, what can happen is that our velocity does not exactly align with our grid. Okay. So schematically it looks something like this. So let's say that we have our grid that looks like this. Okay. And this could be either finite difference or finite volume grid, but for now I'm making it finite difference by focusing on the grid points. Okay. So if the velocity vector was either pointed straight up or straight left to right, then we wouldn't have a problem because we wouldn't have this crosswind diffusion. What can happen sometimes is we could have velocity vectors that go like this. Okay. So they go at kind of a direction that's oblique to the grid. And so what happens sometimes is that because we're using a different sync scheme that's kind of aligned with the grid, whenever we see this, what can happen is that we get some artificial diffusion that kind of makes our result a lot less accurate than it should be. Okay. And so this issue of the crosswind diffusion is going to be the subject of this lecture here. So since we already know how to deal with the first issue more or less, we haven't really dealt with the second issue that well. And the way that we're going to deal with this is that we're going to change our scheme. So instead of using our normal central differencing scheme for the convection term, what we're going to use is a scheme that's higher order. So in other words, it has more accuracy. Okay. So in order to fix this, we need higher accuracy on the convection term. Okay. And so we're going to see how we apply that for both finite differences, and we'll do finite differences today, and then on Monday we'll see how we do this in finite volumes. Okay. So let me write out our usual terms. So our usual way of doing this. So usually when we talk about convection, we have a first order derivative like this. Okay. And so if we do this with kind of our normal scheme, so if you recall from our finite differences chapter, this is the formula that we would use. So we have phi I plus 1 minus phi I minus 1 all divided by 2 delta x. Okay. And if you recall, the accuracy for this expression here is second order. Okay. So second order, for most cases, is actually pretty good. For a lot of the commercial codes out there, they actually aim for second order accuracy when it's convenient. That's kind of like the standard that a lot of places or a lot of codes aspire to. Okay. But we've already seen that this is not the only scheme that we have to discretize this derivative. So we've also seen that we have forward difference and backward difference, depending on if we want to do upwinding. But kind of the downside of using those schemes is that they're only first order accurate, so they're not even though we won't get an unstable solution, their accuracy is going to be a bit low. Okay, but it turns out there's a whole family of different finite differencing schemes that you can use to discretize these derivatives. Okay? So I'm going to introduce to you guys a fourth order scheme, okay, which is what you guys are going to be using for your project. And so what the fourth order scheme is, it's just essentially what it's going to do is it's going to take our derivative and approximate it with a higher level of accuracy. And the way it's going to do that is it's going to pull information from neighbors that are even farther away. Okay, and I'll show you what I mean by that. So the formula is given by this. So we have minus phi I plus 2 plus 8 phi I plus 1 minus 8 phi I minus 1 plus phi I minus 2. Okay? And all this is going to be divided by 12 delta x. Okay. Right. So you can see we have a much larger expression here. Okay? And the biggest difference that you'll see, I mean, besides the value of the coefficients, is that in this fourth order scheme, compared to our second order scheme above, is that we have to get information from our neighbor's neighbors. Okay? So this I plus 2 term and this I minus 2 term, those are our neighbor's neighbors. So our next door neighbors. Okay. So, you can think of this as kind of an additional cost. So, what this means in terms of code is that we have to, include more lines of our code to basically include more coefficients in our left-hand side matrix for these kind of neighbors. So it's going to increase our cost a little bit, both in terms of, the number of lines of code that we write, and numerically, when we go to invert the matrix, the matrix is going to be, have a lot more terms in it, which is going to be more difficult to invert. So this increase in accuracy doesn't come free. There's hardly ever any free lunch in the world, but what we're going to get out of it is we're going to get a higher order scheme that's going to reduce the effect or pretty much minimize the effect of that cross-stream diffusion. Okay. So besides that, I mean, that's that's all there is to it. So what I wanted to do from here is I wanted to work out the homework problem, and I wanted to show you guys what a higher order scheme code looks like. Okay, so this problem is from homework 6. Okay, and it's problem 2B. Okay. So in this problem, we have a two-dimensional or 2D convection diffusion. Okay, so we have 45 d phi dx minus 45 d phi dy is equal to d squared phi dx squared plus d squared phi dy squared. Okay, so right away we can pull off our coefficients here. So we can see here that our u is going to be 45. Okay. Our v is going to be negative 45 because that's the coefficient in front of d phi dy. And then since we don't have any coefficient in front of the diffusion term, we see that k is equal to 1. Okay. Okay. And then what I wanted you to do is I wanted you to write out the equations for two different cases. So one case, three different nodes where you can apply the higher order scheme to, and 2 nodes where you cannot apply the higher order scheme to. And I'll kind of explain what that is in a second. Okay? And so the grid that we're working on is a 7x7 grid. Okay? So it's going to be hard to draw here. Okay. So obviously, I don't want you to write out the equations for all of these because there's a ton of different nodes here. But so what the problem asks you to do is to find 3 nodes where you can apply our higher order scheme, and then 2 nodes where you cannot apply that. Okay. Okay. So to start, let's take the scheme that we took on the other page, and let's plug that into our equation here. And then let's derive an algebraic equation because since we're using a different scheme for the convection term, our algebraic equation is going to change for discretizing this this equation. Okay. So first thing I'm going to do is I'm going to take this equation here, and I'm going to plug in our higher order scheme for the convection term, and then for the diffusion terms, we're going to use the same scheme that we did before. Okay. So actually, let me do this in terms of just general terms. Okay. So instead of 45 and minus 45, let me do this in terms of u and v. Okay. And then let's assume that we have k out in front. Okay. So I'm going to do it this way just so that for your notes and when you're looking at these later, you'll have kind of a general formula that you can just kind of plug and chug in there for the parameter values. Okay. Okay, so let's go ahead and start working on this. So if we plug in our higher order scheme for the first one, so we'll have U, okay? And then for dphi dx, we're gonna plug in our higher order scheme. So we're gonna have minus phi I plus 2, comma j, plus 8, phi I plus 1, comma j, minus 8, phi I minus 1, comma j, plus phi I plus 2, comma j. And all this is going to be divided by 12 delta x. Okay. So you can see, even though the equation that I had on the previous page was for a 1D case, for a 2D case, we know that we just apply the difference in just one direction. So you can see I've incremented the i's. So you can see the I terms go from I plus 2, I plus 1, I minus 1. It should be I minus 2, sorry. Okay. But we've left the j's alone because then the j derivative is going to come once we discretize the v d phi dy term, which is what we're going to do on the next page because I've run out of room here. Okay, so now let's do the y derivative terms. We have v minus phi I j plus 2 plus 8 phi I comma j plus 1 minus 8 phi I j minus 1 plus phi I j minus 2. Okay, all divided by 2, 12 delta y. Okay. Okay, so those are the convection terms. So you can see they're a lot beefier than they were before. Okay. So then now let's plug in further our diffusion terms, which are the same as before. Okay. So we have k on the outside there, and then we have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, all divided by delta x squared. Okay. And then plus phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1. Okay? And all this is divided by delta y squared. Okay. All right. So that's what we get when we plug in all of our finite difference terms. So usually what we like to do at this point is we like to simplify. Okay. And then usually what we assume is that our grid spacing is the same. Okay, so let's assume our delta x is equal to delta y is equal to delta. Okay. And so after we simplify, and then I'm going to multiply it by delta squared, that equation up there. Okay, just to simplify things, and then we get the following expression, which you can use basically to plug and chug. Okay, so I'm going to start on the next page because I'm guessing I'm going to run out of room. Okay. So after you plug in everything, you get the following expression. So you get minus u delta divided by 12 phi I plus 2 comma j plus 2 phi 2 delta u over 3 minus k times phi I plus 1 comma j plus negative 2 delta u all over 3 minus k phi I minus 1 comma j plus u delta over 12 phi I minus 2 comma j. Okay, make that a bit cleaner. Okay, plus minus V delta over 12 phi I j plus 2, okay, plus 2 delta V all over 3 minus k phi I j plus 1, okay, plus minus 2 delta V over 3 minus k phi I j minus 1 plus V delta over 12 phi I j minus 2 plus 4k phi I comma j is equal to 0. Okay. So it's a lot. It's a pretty long expression. Okay. But that's okay. Because ultimately, when we're writing out the equations by hand, we can just plug in numbers for this. And then once we get into code, I'll kind of walk you through how this is implemented. But basically, this just ends up being just some additional lines that add some terms. Okay. So here is our higher order scheme. Okay. But I'll give you kind of one caveat here. And so the caveat is that this only works when we have enough neighbors for this. Okay. And so what I mean by that is that the in order to apply this equation, we not only need to have neighbors on every side of ourselves, but we also need to have neighbors that are 2 away from ourselves, kind of farther and away. Okay. So now we have to kind of ask the question of not only do I have neighbors in order to apply this equation, but do I have enough neighbors? Okay. Because what can happen sometimes is that you can be at a node where you have enough neighbors on 2 or 3 sides of you, but on one side you don't have enough neighbors. Okay, so let's take an example like this. Okay. Okay. So let's look at this node right here. Let me draw one more line here. Okay. So you can see from this node we have neighbors here, 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 and here. Okay. So we have enough neighbors kind of on the 2 north, the 2 south, and the 2 east of ourselves. Okay. But on the west, or the left side, we only have 1 neighbor. Okay. So because we only have 1 neighbor on that side, we can't actually apply our higher order scheme. So in these situations, we have to kind of revert back to our older scheme. And by normal scheme, I mean the equation that we've used previously when we use just a second order central difference for our derivative. And so just to remind you, and just for completeness, that's given by this expression here. So we have u delta over 2 minus k times phi I plus 1 comma j plus minus u delta divided by 2 minus k phi I minus 1 comma j plus v delta over 2 minus k phi I j plus 1 plus minus v delta divided by 2 minus k phi I j minus 1 plus 4k phi I comma j equal to 0. So right now I have kind of equals to 0 on the right hand side, but if you have a source term, then that's where the source term would be. Okay. So let's go ahead and apply these equations to our example. Okay. And so when you plug in all the numbers for the homework problem, you get the following. So you get minus 3.75 phi I plus 2 comma j plus 29 phi I plus 1 comma j minus 31 phi I minus 1 comma j plus 3.75 phi I minus 2 comma j plus 3.75 phi I j plus 2 minus 31 phi I j plus 2 plus 29 phi I j minus 1 minus 3.75 phi I j minus 2 plus 4 phi I j is equal to 0. Okay. And so you can apply this equation for all the nodes that have 2 neighbors. Okay. So the nodes that I picked were, or one of the nodes that I picked was 17. Okay. Because if you look at node 17 in the mesh on the homework, then you can see that you know there's enough neighbors there. Okay. So all you have to do basically is plug in the neighbors that are both 1 and 2 away. Okay. All right. And then for the nodes that don't have enough, you'll see that those are the nodes kind of on the inner ring. So if you look at kind of your boundary or your domain here, you know that on the outermost ring right here, we have to apply the boundary conditions. Okay? And then on the nodes that are in kind of the inner ring from this, so these nodes kind of right here that make up that that kind of perimeter, those nodes are not going to have enough neighbors for you to apply the higher order scheme. So for these ones, you have to revert back to the lower order. Okay. And then again, for the lower order schemes, you just have to use the equation that I had kind of previously on the last page. Okay. Okay. So that's that. Okay. And so what I wanted to do now was I wanted to basically show you what a higher order code looks like, just so that you can kind of see my thought process behind that, and especially since you'll see a lot of these code structures for the project too. Okay. So let me go ahead and share my screen. Okay. So you can see here, this is the grid for the homework problem. So you can see, I picked node 17 right here. So you can see node 17 has 2 neighbors on the left, so it has 15 and 16. 2 neighbors on the right, 18 and 19. 2 neighbors up top, which is 24 and 31. And then 2 neighbors on the bottom, which is 10 and 3. So we're all good here. Okay. Okay. So then now let's take a look at the example that I've posted. Okay. So just like before, we have section 1 of the code, which comprises of all the parameter values. So we can see we define the length of the domain. I'm using different coefficients here because this is the example that I've posted on the lecture notes. So you can see for this ones I have a diffusion coefficient of 3, and my x and y velocities are 10 and 75 respectively. Okay, so then now let's jump into the section 2, which is the meat of the code. So you can see we have our usual nested for loop here. So we have 4I is equal to 2 to nx minus 1, 4j is equal to 2 to ny minus 1. Okay. Remember, the purpose for these lines of code, or for these for loops, is to visit. all the interior nodes. You kind of have to kind of flip your mindset back to when we did finite differences, because I know we've been doing finite volumes for quite a while. But remember, this is how we did finite differences, where we had kind of a modified for loop here so that we only visit the interior nodes. Because when we apply the boundary conditions, those come a bit later. Okay, so then we jump into the loop, and we see that we have this first section of code right here where we compute the ID numbers for my ID and also for the left, the right, the up, and the lower nodes. Okay, so these are this is the same code that we've had before. So this is the ID numbers for all our immediate neighbors. Okay. In other words, all the neighbors that are basically right next to us. Okay. And then to apply the higher order scheme, we have to also get the ID numbers for all of our distant neighbors too. Okay, so you can see I've labeled them as left ID2, right ID2, up ID2, and down ID2. Okay. So to kind of give you, just to kind of tell you how these are referenced in the formula, left ID2 would be I minus 2, comma j. Okay. Right ID2, this would be I plus 2, comma j. Okay. Up ID2, this would be I, comma j plus 2. And then down ID2, this would be I, j minus 2. So that's going to help us in forming the putting the equations into the left-hand side matrix. Okay. Okay. So this next block of code right here, this is just the diffusion coefficient. So you know, I've kind of broken it up into the diffusion and the convection in the x and y. So the first thing we have is diffusion. So you can see diffusion is pretty straightforward since we're using the same differencing scheme for our diffusion term. So we're going to add a 4k to my ID. So this is phi I comma j. Okay, remember that's what my ID stands for. Okay. And then for phi my ID left ID, this is phi I minus 1 comma j. Okay. My ID right ID, this is phi plus 1 comma j. Right. My ID up ID, this is I j plus 1. Okay. And then my ID down ID, this is I j minus 1. Okay. So you can see when you do just the diffusion term, you have 4k for I comma j, and then for all the neighbors, just the immediate neighbors, we have just a minus k. Okay. So we don't bring in the distant neighbors yet, because remember for our diffusion term, we use the same scheme that we used before. Okay. Okay. So then now we get into the derivatives. Okay. Okay. So first we have a we check the derivatives in the x direction. Okay. So let's look at this first line of code here. So this first line of code says that if I is equal to 2 or I is equal to nx minus 1. Okay. So these are kind of very special locations. So these are kind of not the outermost nodes on the domain. These are the nodes kind of on the first interior here. Okay. And so what we're checking here, so if I is equal to 2 or I is equal to nx minus 1, what this tells us is that there's not enough x neighbors to do our higher order scheme. So if we don't have enough x neighbors to do the higher order scheme, what we have to revert to is the kind of the older scheme with our second order finite difference. Okay, so you can see the coefficients here are x velocity, which is u times dx times 0.5, which is divided by 2. Okay, plus or minus. So this is basically our convection coefficients for our old scheme. Okay. So then if that's not the case, if we're not on kind of this kind of inner ring that's on the boundary, then what's happening, or what's the only thing that's left is that we do have enough neighbors. Okay. Okay. And so if we do have enough neighbors, then we can go ahead and apply our higher order scheme. Okay. So you can see here, there are 4 lines of code here. So I have a my ID left ID. So this is the coefficient for I minus 1 comma j. Okay. So you can see that's a minus 2/3 u times dx. Okay. Next, we have a at my ID left ID 2. So this is I minus 2 comma j. Okay. And then going from the equation, we see that that coefficient is a plus u times dx divided by 12. Okay. Next, we have a at my ID comma right ID. So this is I plus 1 comma j. Okay. You can see from the equation that is a positive 2/3 u times dx. Okay. And then finally, we have a at my ID right ID 2. So this is I plus 2 comma j. Okay. And then the coefficient of that from the equation is u times dx divided by 12. Right. And then we can do the same thing for the y derivative. So this kind of follows the same trend. So we check to see if we have enough vertical neighbors, and if so, then we can do our higher order scheme. If not, then we have to use our older scheme here. Okay. And then the rest of the code kind of follows the same recipe as we always did. So we apply boundary conditions, we solve the system, and then we can plot it. Okay. So after watching the video from last time, I noticed that you guys didn't the plot didn't show up because of the weird screen sharing thing. So if you want to see the plot, you can definitely run this code. Right? So this example is basically available for you on Titanium. Okay. And if you want to kind of add kind of the extra comments that I've added here, then you can definitely go ahead and do that. Okay. And with that, that's everything that I wanted to cover yesterday before the internet kind of conked out on us. Okay. So once again, I hope everyone has a great weekend. If you're viewing this kind of before the weekend, please stay safe, stay healthy, everyone. And I apologize again for this kind of format. I definitely don't prefer this. I definitely prefer, doing this live kind of with everyone, just so you guys can ask questions, because I think, that's really valuable. So, hopefully the internet stays stable for the rest of the semester, so we won't have to do this again. Okay? All right, so I'm going to sign off. So thank you guys again for your patience. Thank you for sticking with this kind of strange situation, and I'll see you guys on Monday.